let's look at the parallel connection. And for parallel connection, let's see, first we need to be able to tell whether two elements are connecting in parallel or not, right? We can tell two elements connecting in parallel if they form a loop or mesh without additional elements. So in that case, they are connecting in parallel. So in this figure we're drawing here, and Z1 and Z2, they form a loop, right, or a mesh without any additional elements. So therefore Z1s and Z sub 2s are connecting in parallel. And similarly, Z sub 3 and Z sub 4 are also connecting in parallel, right? And on the other hand, Z1, Z sub 1s, and Z sub 3s are not connecting in series, are not connecting in parallel, or they are not connecting in series either, right? So are not connecting in parallel. The reason for that is, you see, you're trying to form a loop, and you either form a loop through Z sub 4 and Z sub 2, or you can form a loop through this V sub s. In any case, you need an additional element to form a loop. So therefore, they are not connecting in parallel. And similarly, Z sub 2 and Z sub 4 are not either, right? So Z sub 2s and Z sub 4s are not. And so we should be able to tell whether two elements are connecting in parallel or not most of the time. But sometimes the circuit could be drawn in a very confusing way, and then you use this simple rule, right? Whether two elements are connecting in parallel. If they are, whether they form a loop without any additional element, if they are, and then they are connected in parallel, right? So let's look at the equivalent admittance of the parallel connected devices or elements. So here we have Z sub 1s. If we use Z, that means we mean impedance. If we use Y, we use admittance, right? The admittance Ys is always equal to the inverse of the impedance, right? So this is the admittance. And so in this case, let's see, for the parallel, if we use admittance, the equation will be more compact. It's easier to write. So let's see, although we're given Z sub 1s, we can always use Y sub 1s. So in this case, we have Y sub 1s is equal 1 over Z sub 1s, and Y sub 2s is equal 1 over Z sub 2s, so on and so forth. So we're going to use the admittance for this case. Okay, so the element constraint, we can still write the element constraint, element constraints. And in this case, we use admittance, and here I have current is equal Y sub 1s times the voltage V sub 1s, right? And I have a current I2s that's equal Y sub 2s. And this is the same equation, although we're using the admittance, right? The same equation as V is equal I times Z. So because if you divide the Y sub 1 on both sides, so 1 over Y sub 1, that's Z sub 1. So you should make the same good friends with the impedance as you do with the impedance. I sub ns, that's equal Y sub ns times the V sub ns, right? And this is the element constraint based on the connection constraint, the KVL. And since these are parallel connected devices, KVL, and they form a mesh without the third, so in that case based on KVL, we have V1s is equal V2s is equal V sub ns. They are all equal the total voltage. Oh, this is not the phasor, so this should be Vs. Sorry about that. So this should be equal the phasor to the Vs should be equal all the voltage across. So the total voltage as a terminal that should be equal each of the voltages across these elements. And also we have the KCL, right? So at this node here, the current, total current I sub s, KCL, the current I, let me zoom out a little. So in this case, I have I sub s, is, that's equal I1, s plus I2, plus plus INS. So all these entering currents, right? This is the current entering, and these are leaving currents. So the entering current is equal to the leaving current, which is the third flavor of the KCL equation. And we can substitute these things in. So in this case, we have y sub 1 times the v sub 1s plus y sub 2s times v sub 2s and plus y sub ns times v sub ns. And since all these voltage equal the total voltage, the terminal voltage Vs, so I just factor the Vs out. So I have y sub 1s, put a brackets here, plus y sub 2s plus y sub ns, that's equal times Vs, right? That's for the first circuit. And for the second circuit here, let's see if we here we label the impedance, we label admittance, I'm sorry. And in this case, we have is is going to be equal y sub eqs, so this should be a function of s as well, and times the Vs. And if you compare these two equations and the equivalent impedance, so the equivalent admittance, y sub eq should be equal to y sub 1s plus y sub 2s plus plus y sub ns, right? So if you really want the know the impedance, instead of the admittance, so if the z sub eqs for the parallel connected devices, that should be equal to 1 over y sub eq, right? And if you also utilize the admittance rather than the impedance for each element, each of the element, that be 1 over y sub 1 is 1 over z sub 1, right? Plus 1 over z sub 2s plus plus 1 over z sub ns. So this seemingly more complicated, right? But if you use, these are equally correct. Okay, so this is for parallel, this is for parallel equivalent impedance. The only thing is you use the impedance versus admittance. In a special case is that if you have two elements only, let's see, for two elements, I didn't really stress this for the phasor case. Let's see, for two elements, a special case, because many times you're using special case quite a bit. For special case of two elements in parallel, and in this case, let's see, we have y1, let's see, y sub 1s and y sub 2s, and the YEQ in this case, still you can use YEQ is still equal y sub 1s plus y sub 2s, right? But if you are giving impedance, so in this case, let's see if I have z sub 1s and z sub 2s, right? So you're trying to find z eqs. You can still think that way as z sub eqs is equal 1 over y eqs, and y eqs is just 1 over the y eqs is y1s plus y2s. In this case, y1 is equal 1 over z1, right? And plus 1 over z2. So if you multiply the denominator by z1 and z2, and also I need to multiply the numerator by z1 and z2, and what do you get? On the numerator you got z1 times z2 s, right? On the denominator you get z1, this z1 cancel, you got z2 for the first term, and for the second term z2 be cancelled, you got z1. So I got a z1 plus z2, or z2 plus z1. So you got the sum over, so the impedance for the two elements, for two element case, and the impedance, the equivalent impedance is the sum over the product, the product over the sum, the product over the sum. And this thing actually confused a lot of students. I don't know why, but this is this is a quick way of getting this. But if you want to stick to the general expression, that's fine, right? And sometimes this will give you quicker results, sometimes it doesn't. Okay, so let's look at the current division in a moment.